Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed about the perturbation techniques. This means that different kind of perturbations we have discussed. Already we have discussed that in a population dynamics that for different values of R, we have obtained the values like 2.2, 3.3 and 3.33, where we have like the stable solution. First case we have just obtained. For R equals to 2.2, we have just find it that initially it will have a like sharp variation, and after that we have a like a stable variation of the profile. For 3.3 and 3.33, we have just find that it has a like oscillatory profile, but if we have just extend these values up to 3.9, we have just find there exists a chaos. And in this lecture, we will just start about discrete time nonlinear models in population dynamics. So, earlier we have discussed also like discrete time linear models in population dynamics, also some of these models which involves the nonlinear terms that we have also discussed. And in this model, first if you just go for like logistic difference equations, then these equations will involve prey-predator model. So, that we will just also consider for this lecture. And first if you just go for this logistic difference equations, then the general logistic difference equation, it is represented in the form of x n plus 1 equals to r x n into 1 minus x n. So, already we have explained that if we can just take that this product here, that can be represented as r of x n minus r x n square, which just represents the nonlinearity of this equation. And if you will just assume, suppose x n is a very small here, if x n is very small here, then we can just find that 1 minus x n, it will just approximated to the value 1. So, if it is approximated to the value 1, then our model will be reduced in the form of x n plus 1 is approximated as r of x n here. So, the logistic model or this equation will turn out to be exponential growth function for small values of x n. Hence, the linear models which we considered so far are only valid for small populations. This means that when this population will grows it off, if it grows exponentially, then we cannot find a feasible model in a practical sense. Since certain restrictions like sometimes this food or resources, they are limited. Sometimes we can just find that due to like a climate or due to like a huge number of population, they will be declined. So, always we cannot find that this can be just grows it up in a exponential form. Since in a like logistic equation, we have already analyzed that some of these population models which are based only this logistic growth models, where this exponential growth is occurring. And in this lecture, first if you just go for like a nonlinear prey-predator model here, suppose x n be the population of prey here and y n be the population of predator. So, already we have explained that many different models we have just considered, like suppose if a rat is there, cat is there, then we will have a prey-predator model. If suppose tigers are there, deers are there, then we are just assuming this is also a prey-predator model. Sometimes we can just visible that if tigers are there, deers are there, but there is a limited resources of grass there. This means that after certain level, you can just find that the deer population will not grow it off. They can just compete each other to find the resources or the food, and they cannot exist or they cannot like exponentially grow up in that scenario. And if little tigers are existing there, they can eat like this deers, and they can just grow it off. After like certain scenario, you can just find that if the deer population it will just decline, then this tiger population will grows, and at a level they will again start to decline also. So, if you just consider all these scenarios, then we can just find a various class of a prey-predator model, but here we will just analyze like simple points in a simplified model information here. That is suppose recall the linear prey-predator model here, that is x is the only prey and y is the only predator, suppose it is just existing. And there is if there are no predators, the population will grow at a rate proportional to the population of prey. Already we have explained this one. Since suppose like a tiger and a deer are present in a level, and if suppose we are just assuming that there are no tigers there, then this like deers they can just grow up like anything if the sufficient of food is available to them. And sometimes if there are suppose no prey is existing, this means that no deers are present there, then the predator population this will also be declined, since they will not find food and they will just die out. Hence, we can just consider that this predator population also they will decline at a rate proportional to the population of predator. So, that is why usually we are just considering that sometimes this prey population they will grow exponentially, and we can just consider that this predator population they will also decline exponentially. When both are present, if suppose tigers are there and deers are there, then it is a beneficial for growth of predator while harmful for prey. This means that the tigers will eat the deer and the deer will be declined, and the tiger population it will just grow it off. Hence, this predator population will increase and prey will decrease at a rate proportional to the product of these two populations. Since individually if you will just consider like one tiger can like eat 2 deers at a time, then we can just assume that this will just decline in a very fast manner, that deer population. But this tiger population if you just see here, they can also individually depend that how many number of deers are present at that scenario. So, that is why we are just assuming that the decline rate or this like growth rate that depends on the product of both of these two populations. And suppose based on these points, the mathematical model if you just construct in a form like xn plus 1 at a time level n plus 1, if the population of a prey is present as xn plus 1 here, that depends on like 1 plus a xn minus b xn yn. Since due to the presence of a predator here, the prey population declines here, and due to the presence of a prey here, then the predator population that just grows it off with respect to the product of these two population levels. If you just see here, the constants involved here are as a, c, b and d here, and we are just considering that all the constants a, b, c and d it should be greater than 0. And the question arises that why we are just considering all are positive here. So, point wise you will just go for this like discussion. So, first case if you just consider like the constant a here, a represents here that the growth of rate of prey population, especially if you just open this model, you can just find that xn plus 1 it can be written as like xn plus a xn minus b of xn yn here. So, if prey is present, then definitely it will have like resources are available, they can eat and they can just grow it off. So, that is why if there is existence of a prey, then there is a growth rate of prey it will just present there, and it cannot be negative since the growth rate cannot be negative, since like deers can give birth of another deers. So, this means that they cannot kill each other. And second is we have just to consider is C is the death rate of predator population. So, predator population if there is not sufficient amount of prey is present, definitely the death rate of predator population it will just be present there, but it cannot be negative, since there should be some spaces there to get the death rate there, neither we cannot say that it can be like negative. So, if you just consider here B and D which represents the effect of interaction between prey and predator. So, if you will just recall this linear prey predator model, we can observe that since if you will just see here C greater than 1, it will make the predator to grow geometrically in absence of prey species, which is unrealistic. Suppose if you will just consider here prey species is 0. Prey species is 0 means we can just consider suppose here xn is a 0 suppose. If xn is 0, we will have like yn plus 1, this is like 1 minus c yn. And if you will just see here, if c greater than 1, this means that we will have here minus 1 factor, since c greater than 1 means this will just giving you a negative factor here. So, negative of some constant into yn. Especially if you just see our earlier model, then you can just find that in case of a nonlinear growth model we have obtained that yn plus 1, this is represented as in the form of alpha to the power n y 0 there. So, this means that it is just geometrically it is just grows in absence of prey spaces, and if you just see here negatively it is just growing here. Negatively growing means it will just make the sense that it is unrealistic. This means that if the death rate it is just present there also, or the declining of this population it is just occurring there with respect to the population size at n plus 1 level, then this death rate cannot grow in a negative level. So, that is why we have just considered that it is a unrealistic situation here. So, that is why C should be lies between 0 and 1 here. And in the previous lecture also we have learned the stability analysis of first order nonlinear differential equations. Usually what do you mean by stability? Suppose if we are just assuming a like a ball, if it is placed here and we will have this surfaces like this way, then if you just put this ball, then especially it will just go here, 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 and then finally it is just achieved this point. Then we can just say that this ball are in a stable position. But if you will just put this ball suppose here, then it may go in this direction, it may go in this direction, where it will be like moving, we cannot predict it out. So, in that scenario when there is a like stable point is existing, so especially we have just learned if you will just see our earlier lectures, so that the fixed point and co-wave graphs we have just plotted to find the stability analysis of this first order nonlinear differential equations. But there we have like system of two nonlinear coupled equations. Here if you will just see, that is represented in the form of like x n plus 1 and y n plus 1. So, whether we can just use the same analysis here, that is the fixed point analysis or co-wave graphs? Yes, definitely you can use that one, and it can be done through a matrix approaches. So, if you will just go for this matrix approach here, so suppose we will just consider, since we will have like a system of nonlinear equations here, a general system, suppose if you will just consider here m nonlinear differential equations, which is represented as zi n plus 1, this equals to fi z1 n z2 n up to zm n here, and I is varying from 1 to 3 up to m here. Suppose for like two coupled system, I am just two systems we are just assuming here nonlinear systems, that is for m equals to 2, if you will just assume here. So, two fixed points it will occur for both these systems. If you will just assume this fixed points as lambda 1 and lambda 2 here. So, where represents A represents the vector of the corresponding points, then to find these fixed points we need to solve two simultaneous equations at a time. This means that if you will just put here lambda 1 as f1 of z1 n, z2 n we can just put, since two values we can just put it over there. Since these are fixed values here, we can just put it as lambda 1 and lambda 2. Similarly, for lambda 2, if suppose zi of n plus 1 or z2 of n plus 1, if you just put here, that is in the form of lambda 2 here, that is a fixed point also, since especially in a fixed point form usually we are putting f of x equals to x there, or f of lambda equals to lambda there. Already we have discussed these things in the earlier lectures. And if you will just put here lambda 2 equals to f2 of lambda 1 lambda 2 here, to check the stability of the system around these points, since we used to take like a small perturbation and we have just expanded it to make the linearized in a sense using Taylor series expansion. So, we need a Jacobian matrix for this, and the Jacobian matrix of the system of two nonlinear equations can be written as like Jacobian of this matrix A, which is written for two set of equations here, the vectors associated as lambda 1 lambda 2 here. The Jacobian can be written as like a first order difference of f1 with respect to lambda 1, then f1 with respect to like lambda 2, and then f2 it can be differentiated with respect to like lambda 1, then f2 can be represented or differentiated with respect to lambda 2. Especially if you just see here, the variables used are like z1 and z2 here. So, that is why we have just represented this differentiation with respect to z1, since f1 is the first function here. So, then f1 with respect to z2, then f2 with respect to z1 and f2 with respect to z2 here. And if we will just go for a further analysis of this prey-predator model here, that is, if the magnitude of all the eigenvalues of this Jacobian matrix J of A are strictly less than 1. This means that if you will just assume these eigenvalues are less than 1, then we can just say that the system is stable, and if it is greater than 1 or equals to 1, then we are just saying the system is unstable here. And this is already we have discussed in the previous lectures. And if we will just go back to our system here for the nonlinear prey-predator model, the fixed points if you will just see here, that is just given as lambda 1 equals to f 1, lambda 1 lambda 2 and lambda 2 as f 2 of lambda 1 lambda 2 here. If you will just put in this system, then we can just find that lambda 1 can be written as 1 plus a lambda 1 here, since x n plus 1, this is also as a function we can just express as a lambda here. So, lambda 1 can be written as 1 plus a lambda 1 minus b lambda 1 lambda 2. Since corresponding to x we are just putting here lambda 1, corresponding to y we are just putting lambda 2 here. Similarly, if you just put here lambda 2, it can be written as 1 minus c lambda 2 plus d into lambda 1 lambda 2. So, this is the thing it is just written here, if you just visualize 1 minus c lambda 2 d lambda 1 lambda 2. So, by solving, if you just go for the solution of this coupled simultaneous equations here, this means that we are just writing here 0 0 and c by d a by b as the fixed points here. And if we want to go for this Jacobian of this matrix here, that is J can be written as like first difference with respect to lambda 1 here. So, lambda 1 if you just differentiate this term, we can just find that 1 plus a first term here, and second term if you just differentiate here, that is nothing but like b y term we can just write. Since we are just differentiating here, if you just see here, that is nothing but z1 and z2 here, this is z1 and z2. If you just see these variables, accordingly we can just differentiate this one. So, first difference we can just find that one as like 1 plus a minus b y here. B y means with respect to x we are just differentiating that one. Second one if you just see here, that is nothing but differentiating with respect to y here. So, y means we can just find this one as 0, only minus b x n it is just present there. So, that is why this is present there. And third one if you just see here, the differentiation with respect to x, if you just do the second equation, then we can just find here only d y n, dy we are just written here. So, last one it is if you will just differentiate with respect to like y here, then we can just find 1 minus c plus dx n here, 1 minus c plus dx here. So, finally, for these points like 0 0, if you will just analyze the Jacobian matrix, it can be written as like for x equals to 0, y equals to 0, we will have this term 0 here, this term 0 here, and this term 0 here, this term 0 here. We will have like 1 plus a 0 and 0 1 minus a, and the eigenvalues are like 1 plus a and 1 minus c. Since this is like a diagonal matrix, so all the entries are nothing but the eigenvalues here. And for the fixed points, if you will just see here, that is a 0 0, if you will just see, this is said to be stable if you will just assume that absolute value of 1 plus a, it should be less than 1, or if you will just modify this one, we can just write that a simple manipulation if you just do here, that is minus 1, it should be less than 1 plus a less than 1. This implies that a should be lies between minus 2 and 0 here. But if we consider suppose a greater than 0, so the fixed point 0 0 is unstable, since it will just give you a positive value there. Similarly, if you will just go for the analysis of like a 1 minus c here, so sorry, for the other point if you will just see here, since we will have like a 2 points we have just obtained, that is 0 0 and c by d a by b here. So, if you just see for the other point, that is c by d A by B here, the Jacobian matrix which is just written here, that can just take the form, that is directly if I will just put here x equals to C by D. So, x equals to C by D means we can have a C point here, and if I will just put this x equals to C by D here, that is minus B C by D here, and y if I will just put here, then that will just give you minus B into A by B, this will just give you minus A here, and this will just give you dA by B. So, same it is just written here, and the eigenvalues if you will just see here, if you will just reduce this one, this means that we can just consider this one as 1 minus lambda here, 1 minus lambda, and its determinant equals to 0. Then we can just find that lambda equals to 1 plus or minus IAC here, and the magnitude of these eigenvalues are greater than 1, hence the steady state is also unstable here. And if we will just consider a particular example here, suppose we will have a forest where only 2 species are existing, that is only fox and rabbits are living there. Fox are entirely depending on the rabbit population, and if the rabbit's growth rate is suppose 1.2 and that of a fox is 0.4 here, the effect of interaction of both these species on rabbits is 0.5 while on fox is suppose 2. So, if it is asked to formulate a like a discrete time model and calculate the number of each species after 2 years, then we can just apply the previous discussed model. And if you will just consider that model, we can just find, since in that model we have just considered as xn plus 1, yn plus 1. Similarly, we are just putting here the rabbit as R model here and fox as F here. So, if you just see here 1 plus A means, if you just see rabbit's growth rate, it is 1.2, directly we can just put A equals to 1.2 here, and that of fox it is like 0.4. So, B can be considered as 0.4 here. So, the same model if you just see here, yes. So, that is a B, it is considered as like the growth rate due to like both these populations present or declined due to the presence of both these species. So, that is why we can just consider here as like C equals to 0.4 here. So, B equals to like 0.5 and D equals to 2 here. So, that is why we can just write up here as the model as Rn plus 1, this equals to 1 plus 1.2, that is 1 plus A into your rabbit minus 0.5 Rn into Fn, since this will be declined due to this fox population here. So, that is why each of the individual species will be affected by the individual of the other species. So, that is why it is just written in a product form here. Then this fox species at a time level of n plus 1, it can be written as like 1 minus 0.4, since it will be like a declined rate here, and plus this will be increased due to the population of like Rn. Individually it can be affected by the fox population also. So, that is why it is just written as plus 2 Rn Fn here. And if you will just proceed to find this population levels due to this fixed point analysis here, we will get like 2 fixed points here, that is 0, 0 and 0.2 and 2.4. So, directly we can just put here like lambda 1 and which can be written as 1 plus 1.2 lambda 1 minus 0.5 lambda 1 lambda 2. Similarly, we can just write lambda 2 equals to 1 minus 0.4. This is a Fn, Fn means we can just write lambda 2 plus 2 lambda 1 lambda 2. And if you will just formulate this Jacobian, this means that we will just differentiate this one with respect to like x here. If you will just see, this means that we will just differentiate first with respect to r here, then with respect to f. So, Rn if you will just differentiate, we can just find this one as like 2.2, since this is the sum here, 2.2 minus 0.5 Fn, since we are differentiating with respect to Rn only here, minus if you just differentiate with respect to Fn here, then we can just find this one as minus 0.5 Rn here. And similarly, if you will just differentiate this one with respect to Rn here, then it will just provide you 2Fn. Similarly, if you will just find this differentiation with respect to Fn here, this will just give you 0.6 plus 2 Rn. And for fixed points 0 0, the eigenvalues are like 2.2 and 0.6. So, if you will just see here, the eigenvalues are like one of them is greater than 1, 2.2. So, it is unstable. So, for fixed points like 0.2 and 2.4, the Jacobian is represented as like 1 minus 0.1, 4.8 and 1. If you will just see the magnitude of the eigenvalues, it is greater than 1. So, the system is unstable. So, in this lecture we have discussed about this applications of logistic difference equation, then pre-predator model, then like how we can just analyze this nonlinear pre-predator model in Jacobian matrix. Then this Jacobian matrix, it is used for the stability analysis of this nonlinear system. Then we have considered one example based on that like stability analysis to find that exactly how it is just behaving inside the system or in a practical scenario. Thank you for listening this lecture.